Let's take a look at number one here on this little worksheet here. The car is moving at 20 meters per second when the driver slams on the brake and skids to a halt. The brakes can apply 50,000 newtons of frictional force. How far will the car skid? So why would you ever do this kind of calculation? Usually when you're designing traffic flow in a city, somebody's job as a traffic engineer, they actually have these kinds of formulas. It's kind of weird, okay? So anyway, let's break this down here. So the first thing we want to do is make a little sketch in terms of what's going on. So here we have a car and it's moving. What kind of energy does a car have when it's moving? Energy of motion is called, it's called kinetic energy, right? Because it has movement and it takes energy to move a mass, right? And KE, the formula is 1/2 mv squared. Let's go ahead and fill that in, okay? And then when your car drives, a lot of energy is wasted because in real life it's annoying, right? There's stoplights. What's with that? Stop signs, other traffic. So all the gas you burn to get the car moving, ironically, you lose a lot of that, right? And it's lost to braking, right? And in this case, what's that called when the brakes apply a force over distance? That's called what? Force times distance is simply called work energy, right? So technically, a lot of your car's energy is lost to mechanical work. So a cool example is, anybody have one of those hybrid electric cars, or one of your friends has, like the Toyota Prius and all that? Okay. What's cool about that is a lot of those are designed to have kinetic braking. As you brake, you don't just have a brake pad squeeze the wheels there to create friction and stop. You actually, as you brake, there's a flywheel that spins, and as it spins up, it generates electrical power, which you store in a battery. So literally, you're trying to recover that energy as you brake, which is really cool, because there's also less wear and tear on your brake pads, okay? So the future, the sky's the limit, because right now cars are super inefficient, okay? A lot of estimates is most cars are like, I don't know, less than 5 to 10% efficient, and that's only accounting for burning the gasoline. A lot of it's wasted to like heat, right? But if you think about it, a lot of the energy is wasted in just moving the car, because most cars are 2 to like 6,000 kilograms, depending on the size of your car, and you're just like a couple hundred pounds at most, right? So you could think of like 99% of the car's energy is wasted, because all the end is you just want to move yourself, right? And maybe whatever cargo you have. So building super lightweight cars with very efficient engines, that's the future, and that's what we got to figure out, okay? Anyhow, for now, let's try not to kill anybody. Let's break down all the information here, okay? Step 2, we list all the givens here. We're given that the car has a mass of 1,000 kilograms. The 20 meters per second is a measure of the, what did you guys say? Michael, you called it earlier? It's the velocity, that's correct. Fancy word for speed. And we know that the brakes can exert a frictional force of 50,000 newtons, which is about 10,000 pounds of pressure, think of it that way, okay? Because a newton's about 1/5 of a pound, think of it that way. And the question is how far? What's another way to say how far the car will skid? That's the what? The distance, right? And you're saying like, I don't get it. Like, like what equation do I use? Well, there's one big idea equation that ties this whole unit together, and that is the conservation of energy, which simply states that the energy you start with inside any system equals the energy that you go to in the end of the energy transformations for that system. So yesterday we had a very dramatic example with the bowling ball suspended from the ceiling. When you hold the bowling ball up to your face and you let go, you're going to be okay, because if you put in 100 joules of energy, you can only get at most 100 joules back, assuming nothing is lost to heat or friction or air resistance. So you're actually safe, right? As long as you don't push the bowling ball or move forwards. So in this case, what was the energy we put in initially in this system? We have a what? A car that's moving, so that's kinetic energy. So the hardest part is to see what kind of energy is there, right? And then where does all that kinetic energy go when you drive? When you need to stop, you step on the what? The brake, so that goes to what? To work energy, right? And now we can just plug and chug, because KE is 1/2 mv squared, and work is force times distance. We know that the mass is 1,000, velocity is 20, the force is 50,000 times the distance. So if we take 1/2 1,000, which is 50, times 20 squared, which is 400, we divide by 50,000, get out your calculators, go ahead and chug that through. Or if you've already done that, what'd you guys end up getting for the distance? Okay, when we plug in, we get a distance of units, okay? We get 4 meters. Now, in the next part, we don't actually have to do a lot of math. We could plug into the equation, but let's try to do this conceptually, okay? If you double your driving speed to now 40 meters per second compared to 20, okay? We don't actually have to do a lot of math. We can actually figure this out. Notice the relationship between kinetic energy, mass, and velocity is it's 1/2 mv squared. So if you're going twice as fast, what's the extra kinetic energy that the car has? What's 2 squared? It's actually 4 times the energy, right? And in the end, if all that KE goes to work, which is force times distance, then the force is constant. Therefore, the braking distance is how much more? It's going to be 4 times more, or 16 meters, right? How about if you double the speed again? Now we're up to 80 meters per second. So that's what? 20 to 80? That's 4 times the speed here, right? If you think about it. 4 times the speed. Actually, I guess that's double the speed is the way to think of it. So it's 2 squared, right? But anyway, if you have 4 times the speed, it's how much more kinetic energy? 1/2 mv squared is, what's 4 squared? 16 times the KE, right? So if you have 16 times the kinetic energy, you're going to have 16 times the braking distance. 6 times 4 is 64 meters, okay? So if you look at your answers, what happens as the speed increases? If you double the speed, the skidding distance goes up. What's 2 squared? It's going to go up 4 times, right? The whole point is it's an exponential relationship, okay? So the way we can explain the relationship between work and kinetic energy is pretty simple, okay? The kinetic energy we put into the system goes to the work done by the brakes, right? And since kinetic energy is proportional to the velocity squared, if you drive faster, if you drive twice as fast, it's not twice the stopping distance, it's 4 times. So what's practical about this? Very simple. In your neighborhood, what's the speed limit in your neighborhood if nothing's posted? Okay, yeah, be very careful. It's usually 25 miles per hour. In some neighborhoods, it's even 20 miles an hour, okay? And the reason why is it's very simple. In order to stop in time so you don't kill somebody, or like a kid playing in your neighborhood, ball rolls out in the street, if you're going, like if you're an idiot and you drive 50 miles an hour, which hopefully you never do in your neighborhood, right? What's the stopping distance going to be compared to 25 miles an hour? Theoretically, it would be 4 times the distance, exactly. Very, very hard to stop. And in bad weather, like all bets are off, right? Because the coefficient of friction drops, etc. Okay? Now what if we triple our original speed? Last question here, and then we're done. Almost there, right? If you slam on the brakes and you triple your original speed, 3 times the speed would be how much more kinetic energy? 9 times, right? So if originally it was 4 meters, it would take us now 36 meters to stop. And the whole point is we have 9 times the stopping distance there, is the way to think of it. Okay?